Hello, beautiful, wonderful, fantastic people. I hope you're all doing incredibly well. I'm currently back in Perth to hang out with my family and my dog and write my thesis in peace and quiet. But yeah, I'm also here hanging out with Scott. He's one of my oldest friends, both in the time that I've known him and how old he is. And he plays in a couple of really cool bands, and one of those bands is Voyager. And they're doing a really cool gig over in Europe, in London, called SpaceRocksLive, and they're also doing a cool European
UK
tour.
run and a couple of European festivals as well.
That's really, really cool. But, so Space Rocks is a very strange gig that is being hosted by ESA, the European Space Agency, and there is like a couple of cool like progressive rock, progressive metal bands. Mm-hmm. Like Anathema are playing,
Yeah, Anathema and Amplifier.
They're so cool. But there's also a bunch of like scientists and Tim Peake, who's an astronaut, and I just wanted to prepare Scott, so he like.
I don't seem like a complete ignoramus.
You know a lot about music, but I'm not sure how much you know about like space-related things.
I probably know about as much as that escapes from a black hole. That's something.
What escapes?
Nothing escapes from a black hole.
Oh, but here's the thing. That's not right.
Yeah. Okay.
You're right.
Well, in which case I know nothing.
But here's the really cool thing. So light doesn't escape from a black hole.
Okay.
Right. But around the event horizon, you can get this really, really cool thing called Hawking radiation.
Right.
Which is Stephen Hawking came up with the idea in like 1970s, and the basic idea is that over time, black holes do evaporate very, 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 very slowly.
Right.
Through this really crazy thing. Basically, there are virtual particles that pop in and out of existence, but they come created as a particle and an antiparticle. Mm-hmm. Right? So they pop in really quickly, they pop out, they come together, they annihilate. The average like energy is still like conserved. Right? So it's like taking money out of a bank and then putting it back immediately before anyone notices. Right? Right. So like everything's still fine there, right?
Yeah.
But what happens around the event horizon of a black hole, so like on one side, like these particle-antiparticle pairs created, one part, the particle or the antiparticle, will be on the inside of the event horizon, and the other one could be on the outside of the event horizon. Right, so the inside one would fall in and the outside one would fly out.
Right.
We can't get observational evidence for this. It's basically impossible to do that, but we're pretty sure it's right. Because one, the model and the math really checks out, and we can do kind of simulations of this. Instead of the speed of light, we can do it with the speed of sound. Some really, really cool experimental stuff. But yeah, Hawking radiation. So things do really slowly escape out of black holes.
I guess in which case I definitely know nothing about space then.
It's so cool. Okay. So here's, I don't know, maybe like 15-20 minutes of me yelling at Scott. If you're into that, enjoy. Okay, Earth. Flat?
Yeah.
Spherical?
Yeah, flat.
Flat, okay.
I'm a flat earther, yeah. Obviously a sphere. I know that there is no gravity in space, but I know that gravity is also a weird thing.
Okay, I love this so much. Okay, yeah. This is great. I'm glad I prepared very little. First things first, to be a very pedantic scientific asshole, like, well, actually...
technically,
the Earth is an oblate spheroid. Oh, but seriously, it's actually like such a cool thing, because the Earth is pretty close to a sphere, but because it's spinning around, the equator actually bulges out slightly more than the poles do.
And it's because of the spinning.
Yeah, it's because of the spinning. So also technically, if you stand on the equator, you weigh less than you would at the poles. The force that you exert onto the Earth is smaller.
Do you reckon that has an effect on the people who live there?
I don't think so. It's like really tiny.
Yeah.
It's really, really tiny. Also, you said there's no gravity in space.
Yeah.
So I'm gonna like probe you a little bit on that.
Yeah.
So when you say when Tim Peake, the astronaut you're playing with, goes to the International Space Station, that the force of gravity there is smaller than that of Earth, or that it doesn't exist, or that.
Well, I guess I just say it's different.
Okay, cool. I like that.
I mean, that's a pretty diplomatic way of saying. You know.
So the International Space Station, the orbital height, right, is pretty consistently around 400 kilometers, right? So it's actually closer. Like when the International Space Station flies above your head, it's only 400 kilometers away.
Right.
So that's actually ridiculously close. And 400 kilometers in that case isn't enough to actually change the acceleration due to gravity. Right?
Oh, so
it's still like 9.8-ish. It might be like 9.6.
Right.
Right. So we can actually do the calculation on that.
Okay.
But it doesn't affect it all that much.
Yeah.
But what's actually happening is that with the International Space Station flying so fast horizontally, basically the astronauts are falling towards the ground and keep missing. Right?
Wow.
Right.
Okay.
In the same way that the Earth is falling towards the sun.
Yeah.
And keeps
So
missing.
it would be, imagine as if you were throwing a ball.
Yep.
And the ball just keeps spinning around in an orbit.
You know, like, that's really funny because there is a wonderful illustration that Isaac Newton did in the 1600s where he thought of a thought experiment of taking a cannon and putting it on top of a mountain. And he drew, like, the paths of the cannonball.
Yeah.
And in one case, like, the cannonball went so far, right, like that it did an orbit around the Earth.
Right.
But, like, that's what orbital... Like, that's what orbits are.
Yeah, right.
Which is really cool. So there is gravity in space.
That's where... Because there's that whole thing where if you take a watch up into space, the time is different, but it's not actually just the fact that the watch is representing time differently. It's that time itself is
actually different.
Yeah, so that's the part where my brain melts.
Yeah, man, me too. So this is really cool. I really want to do like a full series about special and general relativity sometime. It's not going to be this year because it's like it is way too much, and it's also really hard to explain without introducing a bunch of
really technical.
Yeah, but like without like if you can either explain it really technically, which means that you're doing a fourth year physics course, or you can explain it with a bunch of analogies, but these analogies introduce a bunch of not great misconceptions.
Yeah, totally.
Right.
Totally. It's a hard thing to communicate honestly, but also at layman's level.
So here's where both special and general relativity, right, which were developed by Einstein, really come into play in our day-to-day lives. And most people don't know this, is that anytime you use a phone, right, to use, maps, anytime you're using a GPS, right, that is going to, at least 3 satellites that are up in space.
Yeah.
Right. Due to both the speeds with which the satellites are traveling, and due to that slight change in gravity, them being further away from the Earth, the clocks physically run at a different rate on satellites than they do on Earth.
Right.
Right? And if you don't compensate for that, GPS systems would just not work.
If I could snap my fingers and there was an atom in space that was enough away for time to become a different thing, and it snapped its fingers at the same moment, would we be able to measure that that's the same moment in time?
So if you're asking about simultaneity,
Yeah.
like that's a thing, that doesn't exist. Like there's no such thing as a simultaneous moment in time.
Right.
Which is kind of insane and plays a bunch of havoc with what time actually is.
Yeah,
and the philosophies
I guess
of time.
the way I'm thinking about it is if you've got 2 conscious people experiencing something at the same time, but one is a light year away, are they experiencing that actually at a different time, even if the moment is the same?
But there's no such thing as the same moment.
Okay.
Which is right.
That's okay. Well, in which case, I don't understand. Yeah, right.
And due to missions like Kepler and TESS, we've learned that there's thousands of extra. They're called exoplanets, extrasolar planets.
Yeah.
Right. So there's thousands and thousands of of planets that are orbiting around other stars.
Yeah.
Which I think is really neat.
Yeah, totally.
Cool.
I actually had a question about that
Yeah,
because when you look at stars in the sky, would it be safe to say that there are planets orbiting around those stars that you're seeing out there? Because that sounds like a stupid question.
No, it's not. It's a great question.
But it's interesting because when you look at the star, you only acknowledge the star, but in reality, there's probably a bunch of stuff around it that you're not seeing.
This is really great. So that is, and this is going to change over time. Like, we're gonna get more and more data about this. But the last I heard is that it's relatively safe to say that for every star, there is on average one planet.
Right.
That is not to say that every star has a planet.
Yeah, yeah.
That is to say that when a star has a planetary system, it tends to have more than one.
Yeah.
Right, so we have 8. Hey, so it's currently the Peter that is editing this video, and it's already, like, I'm not even halfway through the footage, and it's already, like, 12 minutes long, so that's way too long for one video. So this is going to have to be part 1 out of, a 2 or 3 part series. We'll see how we go. If you like these kind of more casual, longer form videos, let me know. They're really fun to make for me. But yeah, if you like them, please tell me. I'm actually really excited about Space Rocks. I think it's a really, really great event to have, music and science right next to each other, in this really beautiful... Like, for me, science is a part of culture, and to have an event that kind of acknowledges and celebrates that is really great for me. So if you're in London, you should go. It'll be amazing. You should support Space Rocks. You should support ESA. And yeah, please check out Voyager and Scott's other bands. He has like 12. They're all wonderful. So yeah, all the links are going to be in the description. Thank you so much for watching. You guys are wonderful. Peace.